Um, you have more or less 50 minutes plus 10 minutes of questions, okay?
Okay, thank you. I guess everybody hear me well. See my screen. So thank you for the invitation. It's a huge pleasure to be here. I am originally from Cuba. Until the start of my PhD, I was there. So it's an incredible pleasure to be in a seminar of Latin America researchers. I'm very happy. I'm very nervous to be here. There are things like I've been in France for a while now, and in France we have a beautiful tradition of speaking French, even in the seminars. So I don't promise that some French word will be included during my talk. I want to talk to you today about some functional central limit theorems for Erdős-Rényi random graph and the geigen component, the size of the geigen component, which is a work I've been doing in these last years in collaboration with Vlad Limic, which is in Strasbourg, and Sophie Lemaire, which is in Erdős, in the south of the Paris region. You can interrupt me anytime if you have questions. The process I will be talking about, it's the Erdős-Rényi random graph, or it is related to that, where we have n, small n is the number of vertices, and we have p, which is the probability of a given edge to exist or to be open. And this probability is between 0 and 1. And we have the events, e.g. is open or closed, are independent for different values for different pairs of vertices. And the general idea for this process that was introduced by Erdős and Rényi in 59 is to take Pn, so the probability dependent on n, and study what happens when n goes to infinity. For instance, we can take Pn as here as C divided by n, which is called the sparse regime, and look to what happens in that case depending on the value of C. And you can ask several questions. For us, the main question today will be, what is the size of the largest component in the graph? This is for every fixed P, you have a graph, but you can also do like a percolation type construction where you will make a kind of coupling of all the different Erdős-Rényi random graph in one process. And this is done taking, for each pair of vertices, you take a uniform random variable between 0 and 1 independently among them, and define the event E is connected to G with probability P if this random variable is small or equal than the value of. So this is an event that has probability P for every P, and at each P, which is now like kind of a time, you will have a graph depending on the value of the uniform random variable. And this construction is monotone in the sense that if you have P1 smaller than P2, then if you are connected at P1, you will be also connected at P2. And in this way, you obtain a graph value process, which is increasing in the sense of the inclusion of graphs. And at each instant P, you have a copy of the Erdős-Rényi random graph with n vertices and connection probability P. So you go from a static random object to a process whose marginal law of each instant is this static process. So this is pretty standard. So this is what we just described. You take the uniform, you look to these events, and then you construct the graph. And you can do a handmade simulation, taking, for instance, 5 vertices. And then at 0, you have the empty graph. At p equal 1/2, you have another graph. And then at p equal 1 divided by 4, you have another one. And in the end, you will have the complete graph when p is large enough. And as we said before, for every p, you have this identity in law. The process, the marginal law of the process is the law of the Rényi with n vertices and probability of connection p. And for this graph, one of the very well-known results is the phase transition, where if you take n vertices and the probability of connection is equal to c over n, and you said that xi is the size of the ith largest component, then if c is smaller than 1, then you have that the size of the larger is of order logarithm of n. So it's very small in compared to n. If c is equal to 1, exactly when p is 1 over n, and you take n large enough, then the size of the larger is of order n power 2/3. And if c is larger than 1, then the order of the largest component is n. So when c is smaller than 1, you have a picture like this one, when you have several small components, but none of them is even of medium size because they are very small. When c is equal to 1, you start to see some medium-sized component as this one or this one here. There are several of them. Actually, if you look to the first two components of the first three largest components, you will have the same phenomenon. All of them are part of power n2/3. And if c is larger than 1, then all these medium-sized components will collapse and will produce a component of size of order n. This is something very well known related to the phase transition in the Rényi random graph, and we can also see it as a phenomenon for the process that we construct. So this is another picture telling the same thing. If you take in this line, you take c divided by n, then before 1 over n, you are of logarithmic size. At 1 over n, you are of size n2/3. And if c is larger than 1, then you are of order n. And during this talk, we will be here in this region. We will be in the supercritical regime. This is, in green is the subcritical regime. In blue, we have the very critical regime. And in red, which is the focus of our talk today, is the supercritical regime. And in this regime, it is known that if you divide the size of the largest component, you divide by n, then which you will converge in probability to a constant rho c, where rho c is the solution of the equation phi c equals 0 for the function phi c defined like this expression. And you can do a plot of rho c, so it is 0 before 1 because you don't have a component of size n, and then after 1 it increases up to 1. So for every c larger than 1, the size of the largest component converges to rho c, where rho c is the solution of this equation. And you can now, since you have a kind of law of large numbers, you can now look to the fluctuations of these conversions. And Stepanov in the 17th, actually in the year 17, and then Pitel in the 90 proved that for every c larger than 1, if you take the difference between the proportional size of the largest component minus the limit, and you multiply by a square root of n, then you will converge in law to a normal random variable with mean 0 and variant sigma square of c, where sigma square of c is given by this expression here. So you have rho c, 1 minus rho c, and this other expression in the denominator. You can do a plot of that. This is only defined for c larger than 1. So here you have 1. And this is a result for c larger than 1. And then when you approach 1, the variance function goes to infinity, and it continues to decrease after 1 up to 0, which is the limit. So you have that it goes to infinity when c approaches 1, and then it goes to 0. This is like a marginal marginal central limit theorem, in the sense that for the process at each instance c, you have this normal distribution of the limit, and then you can ask, what does it happens when I take not the marginal law, not a fixed c, but I take the process that I defined before, this process here, the size of the largest component of the Erdős random process divided by n. I subtract the limits and I multiply by the square root of n, and I consider c in an interval contained in 1 infinity. So we know that the limiting process needs to have this actually this marginal law needs to be Gaussian, the marginal law with this variance, but it is not clear what process which satisfies that. And this was solved in 2023 by Nathaniel Enriquez, Gabriel Faraud, and Josué Lemaire. This is a paper that was published this year, but the preprint was from 2023. And they say that if you take 1 smaller than c, smaller than c2, and you take this process that we defined before, then you will converge to this Gaussian process here. So it's 1 minus rho c divided by the same denominator we have in the expression for the variance from Stepanov, and then a Brownian motion evaluated in this function. The proof they used was to a very detailed study of the infinitesimal increments of the process given by the largest component, conditional on the largest component at each instant, and they managed to prove that it was a process solving a differential equation whose solution was this object here. And what we did with Sophie Lemaire, which is the same Lemaire here and here, and Limic at the end of last year, was to find an alternative proof for this result using not this idea of infinitesimal increment, but a kind of encoding of the evolution of the connected components of the graph. And that's the topic of my talk today. Before finishing with this slide, I wanted also to remark that we have an alternative expression for the limited process, because if you take this guy in green here, then it follows the same law of a Brownian bridge evaluated at rho c. And in the sequel of my talk, I will discuss this other proof of the result, and it will become more evident why the Brownian bridge appear here. So our goal today is to show an alternative proof of this result that we did with Sophie Lemaire and Vlad Limic. Also, the methods we use, we will discuss today, will allow us to go beyond the supercritical regime. Because in the picture I showed you before about the phase transition, I talk about subcritical, critical, and supercritical, but you can do like a zooming in this initial picture, and if you zoom in, you will have something more happening here around the criticality point. And what happened there is that you can also, if you take the probability as 1 over n plus something like Tn minus 2/3, minus 1/3, sorry, divided by n, then you are still in the same condition where all the connected components, the largest and the second largest, the third largest, and so on, out of order n power 2/3. But you can also take p equal to 1 over n minus epsilon n divided by n, where epsilon n goes to 0, but if you multiply it by n 1/3, it goes to infinity. So you are not at this regime, you are not at this regime, but you are somehow in between both. And this was called the barely subcritical regime. You can do the same in the supercritical. And then if you take p as 1 plus epsilon n divided by n, where epsilon n goes to 0, satisfies the same condition, and epsilon n multiplied by n over 1/3 goes to infinity, then you are in the barely supercritical, and you are like just after the critical regime and before the supercritical regime. And in these both cases, there are also some known results that come from Bolovas, Lushak, Nashmias, and Perez, which they prove that in the barely subcritical, for any E larger than 1, for any E fixed, the ith largest component at this point is of this order, logarithm of n multiplied by epsilon power 3 divided by epsilon power 2. And this conversion probability to a constant, to the constant 2. And if you are in the other side, in the barely supercritical, then the largest component is of power n multiplied by epsilon. It converts, you divide the largest component by that, you converge in probability to 2. And for any other E, the ith largest component have the same behavior like in the subcritical regime. So here in the barely subcritical, you don't have one component that is much larger than the other ones, but you do have that situation in the barely supercritical, where the largest component is considerably larger than the other ones. And we also managed to study this regime. This is the same we just discussed. And Pitel and Wormald and also Bolovas and Riordan, they prove that if you divide the largest component by the right factor, n epsilon, and you take here this as the as a kind of compensator for this random quantity, not in the sense of martingale, but in the sense of to have something that goes to 0, and you multiply by this guy here, n epsilon third, which goes to infinity, then you converge in law to a center Gaussian random variable with variance 2 divided by t for every positive t. And what we prove in our preprint is that if you consider now the process in the barely supercritical regime, So the size of the largest component at time 1 plus t epsilon n divided by n, and you divide this by the right quantity, and you subtract the same guy here, and you multiply by the same factor. Then, as a process, you will convert to something whose marginal law is the normal 0, 2 divided by t. But in this case, it's simply 1 divided by t multiplied by a Brownian motion at time 2t. So we have a similar phenomenon, except that the process is different. And the methods for proving this and for proving the supercritical one are very much similar. So what I will show you in a bit is how we prove that. So a proof for the supercritical. For the very supercritical, I will just show the basic ideas, but it's pretty much the same. So we won't work exactly with the same coupling we described before, this Erdős-Rényi process, where you have the uniform random variable for each pair of vertices, telling you if the edge exists or not. But we will do a small a time change where we take t as 1 minus the logarithm of 1 minus p, and then this event, uig smaller than p, will transform in eig smaller than t, where eig are exponential rate 1 random variables. So you can see this here as a time change of the Erdős-Rényi process, or simply you take two vertices and you decide if the edge linking them exists or not, depending on this event here. If the time is smaller or not than an exponential random variable. And doing so, we obtain another process, which is a time change of this process here, but it is a Markov change, because each change, each transition comes after an exponential time, because it's the minimum of all the edges that needs to arrive at that time. So you have a Markov change that at the beginning have 0 edge, so n vertices with no edge, and each edge appears after an exponential with rate 1 time. This is a different process, but it is Markov, so that's nice. And also in the sparse regime, when t is the probability is t divided by n, this process and the Erdős-Rényi process are the same, because the difference between the probabilities existence of edges for this is very, very small. So for now on, we will work on this setting where we have this Markov process that decides or where the edge appears for any pair of vertices after an independent exponential random variable. And if you have that, the other nice thing is that, for instance, if you have now you are in a state where you have these two components, the first one of size 3 and the second one of size 2, and you ask yourself when these two components will collapse, they will merge, an edge between them will arrive, then this will happen after a random time, which will be the minimum of several exponential time, independent exponential time, for all the exponential between s and t, where s is all the vertices in the component ci, and T is all the possible vertices in the component CG. And because of the property of the exponential, this will be distributed as an exponential random variable with rate equal to the product of both sizes. So at this time, you will have this and this edge that could appear, this and this one, and this one and this one. In total, you will have 6 possible edges, which is the product of 3 by 2. And when that happens, when those components merge, they will produce a connected component of size equal to the sum. So if you don't look to the graph, if you only look to the size of the connected component in the graph, then you will have a process called multiplicative coalescence. Well, initially, you will have the size of the vertices. You can take, for instance, that all the vertices have size 1, and then you will have this kind of transitions where, given a vector, you will go to another state where you take 2 components of the vertex and you sum them, and this will occur with rate equals to the product of the sizes of those components. So in the beginning, if you have a final vector, they will start to collapse, and in the end, you will have a single component of size equal to the sum of all the components. And the rate of collapsing will be this product here. So that's the multiplicative part of the name multiplicative coalescence, and coalescence because you have components that will merge. In the 1917, Erdős wrote a very important paper for the random graph community. In this paper, he talked about the multiplicative coalescence, and he introduced an inhomogeneous random graph model where he said, okay, we don't need each edge to be of size 1. We can consider the edge to be of any size, any positive side, I, and then the edge between I and G will appear after an exponential time of rate xi xj. So you have something that is more general than the Erdős Rényi. The Erdős Rényi is the one that you get when all the xi are equal to 1, but it works well for any other configuration. And in that sense, you have like kind of an equivalent. If you have a multiplicative coalescence, it is related to the evolution of an inhomogeneous random graph. And if you have an inhomogeneous random graph, the process that registers this evolution of the size of the connected component is a multiplicative coalescence. And why is that? What that is important for us? Because for starting the largest component of the process we define, we can simply study the 1 over n multiplied by the size of the first element in the multiplicative component started from 1, 1, 1 n times and 0 after that. So we have a vector of n component of size 1. You make evolve the multiplicative coalescence, and at time t over n, you take the first component of that vector, which will give you the size of the largest component, and you divide by n, and you have the process you wanted to study. But you can also take this 1 over n and include it in the size of the component at the initial time. So you can start the process not from this configuration where you have 1 each time, but a configuration where you have 1 over n times. All the size of the vertices are 1 over n. And then if you want to look to what happened at time t over n for your original process, since you have these sizes here, and the any edge is produced after an exponential xi, xg time, then you will need to multiply by this n square here. So this n square is related to the size that you took initially. But you can simply look to the multiplicative coalescence at time t multiplied by n, where initially all the vertices are of size 1 over n. And this is the approach we will follow. We will study this multiplicative coalescence. We will show now how this is encoded by a process called simultaneous breadth walk. And then we will show how using this, we can prove the main result that we had before for the supercritical regime. So let me introduce the simultaneous breadth walk. This is a process that was defined by Limic in 2019. And this is based on this paper of Erdős that I talked to you about before, and also from some work in the PhD thesis of Inés Almendariz and Jerónimo Uribe Bravo. The idea is that you take x as the vector of initial masses of your graph. For the Erdős range is 1, 1, 1 n times. For the modified version we discussed about before is 1 over n times. And you construct this process here. So you have x is a vector, t is a time, which will be the time of the multiplicative coalescence, and s is an auxiliary parameter now that will disappear in the second half of the slide. And you take the sum of all the values I larger than 1, xi, and then the indicator of this random variable ci divided by t is smaller or equal than s, and you have a constant drift of minus s. And ci is an exponential random variable of rate xi. So this xi here is somehow also related to the rate of the exponential inside the indicator. So you have a jump of size xi arriving at time ci divided by t, and you have this constant drift here. So the process evolves more or less like this. You have this constant drive minus 1, and at some point you have a jump, and you start to decrease again until you have another jump, and then you decrease, and at some point here you went over the same point where you had your first jump. And the length of this so this interval here is called an excursion about past infima of the process, because you were larger than the value here until this point, and you take this interval and you measure its length, and you do the same for the second excursion and to the third excursion. Since you have a constant drift equal to -1, the length of this interval is exactly equal to the sum of the two jumps that you made here. Also here, the length of this interval is equal to the length of the jumps, and here the length of this interval is equal to the sum of the three jumps you made. So you take the simultaneous breadth walk, set t, you take yt as the order length of the excursion of the simultaneous breadth walk, and you can prove, this is a claim that was proved by Limic in 2019, that for every t, yt is equal in law of the multiplicative coalescence started from x at time t. So you have a marginal characterization of the multiplicative coalescence using the length of the excursion of your process. This is not very surprising. So it's a bit like natural for people in the random graph community, because encoding the processes by this kind of work has a very long tradition. This was for example, the methods used by Aldous in 98. However, the surprising fact is that this is not only marginal, this is only also dynamical, in the following sense. You take yt as the order length of the excursion of your process. Then you have this claim that we had before. And now you define y0 equals to x, which is the natural choice, because when t is very, very small, the excursions that you process, that the simultaneous reference work we made, will be all of one jump. So you will recover the vector x. And then you have this strong claim, which says that yt as a process is equal in law to xt. So the evolution of the size of the excursions about past infima of the process follows the law of the multiplicative coalescence started by x. And this is very useful for us, because now if we want to study some properties of the multiplicative coalescence, we only need to look to what happened to the excursions of our process, and this dynamically. So I will now try to show you how to prove the result that we already stated before. So this is what we have in our preprint, but it's the same result from the paper of Enriquez, Faraud and Lemaire. You take ln as the size of the largest component in the graph at time cn, and you fix C1 larger than C0 larger than 1, and you look to this process, which is the size of the largest component divided by n minus rho c multiplied by the square root of n for c between C0 and C1, and this converge weakly in the sense of the Corujo topology, the usual topology, to xc, but xc is equal to this factor multiplied by the Brownian bridge at time rho c. And we will now recover all the preliminary results we discussed. We will, first of all, we will calibrate our simultaneous breadth work. This construction of the breadth work was for any vector xi. Now, since we are in the Erdős Rényi case, we will take the vector as 1 over n times. And then the time of the multiplicative coalescence that is interesting for us is c divided by n, but multiplied by n squared, because you include the n in the size of the component of the vector of initial masses. And then the time that you need to look is c divided by n. So now, if you take this vector and this time, and you plug them on the definition, the general definition of the breadth first walk, then all the xi are equal to 1 over n, and this xi, which was here because I am saying there that all the ci are exponential of rate 1, and I multiply by xi here. So this is an exponential of rate xi. And then you change t by its value, c over n, then you have something like that. the n will simplify, and you will have a very simple process. You will have 1 over n, the sum from 1 to n of this indicator, well, all the CI are of rate 1, divided by C, this less or equal than S minus S. So even if the details up to this point could be a bit complicated or hard to follow, what we simply need to know now is that if we want to know what is the size of the largest component in the Erdős range random graph that divides by n, you simply need to look to the largest excursion of this process. This process is very simple because it's like an empirical process of a sample of size n of exponential random variables. And this is the thing that you can do using the law of large numbers. You know, you can get that this Z and C converge in almost surely to this function here. And this is not new for us. This is simply the rho C that we use at the beginning. And in fact, using Glivenko-Cantelli, you have the uniform conversion, nor a conversion for each C, for each S, but a conversion uniformly in S. And since you have that, so you have that the simultaneous reference work, which is the curve in solid line in the graph here, converges to rho C, which is the curve in dashed lines, then the length of the excursion will also converge. And you recover very easily that 1 over n multiplied by the size of the larger component, which will be the length of the excursion of the simultaneous reference walk, converge to rho C, which is the solution of this equation. And you got that in a few lines. Of course, you are using very strong tools. And also, for free, since this process is a process increasing in C, and its limit is continuous, using Dini's theorem, you have that this conversion is also uniform in C. For every C larger than, but you can take larger than 1, but larger than 0 works also good enough. And now you have that, you have this kind of law of large numbers. The idea is how to go to the functional central limit theorem. So to do that, what you do is you take your simultaneous breadth-first walk and you subtract the limit that we just found, you multiply by the square root of n, and then if you do that, you have like the empirical process minus its limit, which is the cumulative distribution function of an exponential random variable, multiplied by square root of n, and Donsker theorem tells you that the limits will be a Brownian bridge change of time by the distribution function here, fc. And this is the Brownian bridge that appear in our statement of the theorem. So somehow you are just clarifying a bit why there is a Brownian bridge there. And this is a technical claim that we will not go into details, but this works because there is a probability space where this conversion holds almost surely. This is kind of, you are using like the representation theorem, but also simultaneously in C. So this conversion that will be almost surely works for every C larger than 1. Somehow no, but what is happening here is that you have the simultaneous reference work that will be the blue curve here, and you have its limit that will be the red curve. And if you look in details, you will know you know that the size of the excursion above past minima infima of the blue curve should be close to that of the red curve. Here is like some larger plot of what there was before. So at the beginning, you like, for example, for instance, here you do like small excursion, and then you have your very large excursion that goes from here to here to this point in this. So this is like a sum of this part, and this is like a sum of this part here. And then you want to control the difference between the size of the excursion of the blue curve and the red curve. The proof goes like this. You have a square root of n that multiplies this difference. And then using the mean value theorem, you have like this difference is equal to phi c evaluated on the same argument and divided by phi c evaluated at some point c. Well, this is not related to the exponential. It's bad notation for me. But this is a point between these two guys. And thus, then because in the limit this is convergent to this, then you have that this guy here and the argument of the derivative is very close to rho c. So this expression is close to this one here, where we simply change the argument of the derivatives by rho c. And if you compute the derivative of this function and you apply rho c, you get this guy here. And now, because the difference between the simultaneous reference word and its limit is very small, and also because this guy is close to this guy, you have this kind of approximation that is good enough for us. The first term is very small, and this guy is 0 by definition. And then you have, in the end, you obtain that phi c evaluated here, which is this guy, is very close to the pre-limit object, the simultaneous reference word, evaluated on rho c. And thus the change I'm doing on the second line. Also, there is a -1 that appears because there is a -1 here. And then when you take limits, the limit of this, when n goes to infinity, you will go to the Brownian bridge, evaluated in fc, which is the cumulative distribution function of the exponential random variable, evaluated in rho c. And this -1, we multiply the denominator, and you will get this guy. And now, if you evaluate fc in rho c, you will get simply rho c. Rho c is a kind of fixed point for the cumulative distribution function, because it's, I recall that by definition, we have that rho c in x is 1 minus exponential minus cx minus x. So rho c in rho c is equal to 0, and this is simply fc in rho c minus rho c. And this is where we are using in this last part. And the proof is concluded. So the idea is that the simultaneous reference word gives us a nice explanation, a nice proof, but also a nice explanation of why the limit object is this guy. And if we go back to the barely supercritical regime, just for a minute, then I recall the barely supercritical was this case when you have 1 plus epsilon n divided by n, epsilon n satisfies this condition. And we prove that the limit object, in this case, if you take this guy, is 1 over t that multiplies the Brownian motion evaluated at 2t. The proof goes more or less the same. There is some difference, but the central idea is the same. Now, since the constant here is n epsilon n, then the initial size of the vertex you take as this quantity, and then the time of the multiplicative coalescence will be affected by this product of this square. And you do that, you plug those in the definition of the simultaneous reference block, and now you get this process, which is not an empirical process, but still you can somehow study it. If you take, for instance, the expectation and you divide by epsilon n, then you have this process here, which is the same phi than before, but instead of c, you have 1 plus t epsilon n, and this converges to this parabola. And the main lemma that we use is that, okay, this conversion is as before, and if you multiply by a square root of n power epsilon n power 3, this difference, then you will converge to a standard Brownian motion. And this is the standard Brownian motion that appears here. So it's more or less the same proof. Some final remarks. The simultaneous reflex work shows to be a sharp tool for studying the dynamical fluctuation of the barely supercritical regime and the supercritical regime. Actually, David Clancy Jr. in 2025 also used similar arguments, very, very similar, for an inhomogeneous random graph process in the supercritical regime. And this is kind of a remark. As a future work, Puchalski 05 studied the static fluctuation, not only for the size of the gigant, but also for the size of the gigant, the number of surplus edges, and the number of connected components. And in this work, you will find the explicit expectation of variance of the limiting process at a fixed time. So we have a work in progress with Enriquez, Faraud, Lemaire, and Limic for the dynamical fluctuation. So we wanted to kind of get what will be the three-dimensional fluctuation process, limit fluctuation process of when you consider the size of the layers, the number of surplus edges. This is the easy part. But what we have really has occupied over time is include the number of connected components because it's more delicate. And in this other preprint, I also, and using different methods, I managed to study the fluctuations, the dynamical fluctuation of the number of connected components, but in the subcritical regime. So when C is smaller than 1. For the supercritical, as I said before, it's more complicated because there is more dependence between the fluctuation or the size of the largest and the number of connected components. These are some bibliography items that I mentioned during the talk. And this presentation is based on this preprint. And I include here in the end two sources that I think are very nice if one wants to learn some basic facts about the Erdős range random graph and random graph in general. The book of Renko van der Hofstad and this master course from Nicolas Courien. which is very nice, I think. So thank you a lot for your attention. I hope you enjoyed the talk. Muchas gracias.
So, thanks for the talk, Josué. I would like to ask if there is some questions or comments.
Maybe a question on what's expected in the subcritical regime. So do you expect to have also dynamical fluctuations that are represented by a Brownian bridge, or do you expect something different?
In which regime? Sorry.
If you look at the number of critical components in the subcritical regime as a function of well, I guess you have a CLT if you fix C, but if C varies, what do you expect to see as a process depending on C?
Yeah, I think I understood. So you mean like here for the number of connected components?
Yes, yes.
Yeah, in that case, it's already proved in this other preprint that I mentioned. It is of this year too. If you take the number of connected components at times C divided by N, I would call it K, and then you divide by N. So the limiting there is 1 minus C over 2. And if you take that and you multiply by square root of N, then you will converge to a Brownian motion in C divided by 2. So it's simply a Brownian motion with this small change of time. And it's very simple, the proof actually. It's as we discussed today, the multiplicative coalescence is behind all of this, which is a Markov process. And as a Markov process, it has associated a martingale problem. And then you can see K as a test function for this martingale problem, and you find the conversion. It's
okay, so a priori, if I understand well, like C smaller than 1 is easier than C bigger than 1.
Yes.
Yeah.
Yes.
Okay.
We could say that C smaller than 1 is easier, because when C is larger than 1, what happened here is that you have a giant component.
Yes, yeah, okay.
And you have a small components there. And then what will happen when you add a new edge, you can have a surplus edge, which is an edge between two vertices that are already connected. So this is not a problem for us. What is a problem for us is the difference between this connection, which is a connection between two components that are not gigant, that also happens, and this connection, which is a connection between the giant component and the small ones. And these two are different kind of situation, and the second one, and also the first one, are related to the size of the giant. So it's a bit, it appears to be simple. That's the frustrating fact here. It seems to be simple, but at least it hasn't been simple for me to try to characterize the dependence between the evolution of the size of the giant and the number of connected components. But if you are in the subcritical, then you don't have that situation at all, because you don't have the giant component.
Okay, and perhaps another question: if you take epsilon n equal n to the minus 1/3, okay, and then you can allow t to be negative even I guess here, if you look at the largest component, like a priori, you can have, okay, I imagine in principle, you can have a process in the limit, but it has jumps, right? It can have jumps because sometimes the identity of the largest component can change.
You mean here?
Yes. If you have this, do you know what the process looks like?
Yeah. Actually, it's if someone needs to write the history of math, it will grow. You will grow this, and then you will focus here. Well, this is what happened, but somehow, but the fluctuations here is more recent topic of research. But what happened here has been known already for a while. So
even as a like not for even if you look at things as a process indexed by t, not any margins. Okay.
Yeah. And that's true. There is a huge difference. The difference is that in the supercritical regime, what it was here, yes, you have the conversion to a constant, so it concentrates to a constant. But in the critical regime, you are over here and you do the same, except that the right power is n to third. Then you will converge to a random quantity. So it doesn't have, you cannot look to the fluctuations, but you can look to the convergence to the random quantity. And this paper I mentioned from Erdős, what he did was to consider this time, and he characterized the random quantity here for a fixed t. This is the paper of Erdős 97, and there is also 98, which with Limic, not only Erdős. This is the PhD thesis of Vlad Limic. And then the other paper I mentioned, Limic 29, what she did was study this as a process using the simultaneous work. So this tool that I presented you today, the simultaneous work, was constructed to study this regime, to study the very critical regime. And what you get as a process is that the size of the excursion as given by the size of the components are given by the excursion of the process. And in this case, the simultaneous work will converge to a Brownian motion with a drift. And then the size of the largest component on the Erdős range random graph will convert to the size of the excursion of this Brownian motion with drift. It's a beautiful result, a bit difficult to explain, but very well established now. I don't know if that answered your question.
Yeah, thank you very much.
What was your name? Sorry, it's a bit frustrating in the video seminar.
Hubert asked the question. Hubert Lacoin asked the question.
Okay. Thank you.
Now, I have another question which may not make sense, but I would like to see in which time scale you fix the largest component. So can you define a time scale in which at a certain point where you have many competing largest component up to someone at some time, you have one which will remain the largest forever? You mean what I say?
Yes, I think that, well, I am definitely sure that in the supercritical regime, the largest component is.
No, it should be before that, yes.
But I will say that is in the barely supercritical. So I'm sure that here, if you once there is a component of size n, it remains the largest one forever after. But I think that it actually occurs here in the barely supercritical.
Okay, thank you.
You're welcome.
Are there more questions or comments? If not, let's thank the speaker. And see you next week. Thank you for the talk, Josué.
Thank you for the invitation, Gerardo.
Okay.
Thank you for the talk. It's very nice.
Gracias.
Gracias, Josué, muy lindo.
Gracias, un placer.
Uh-huh.